Advantages: transmitting information using fiber optic technology is accomplished by sending pulses of light, which are modulated to carry information through an optical fiber. Fiber optical cabling for data transmission became commercially practical in the 1980s with the development of high-purity glass fiber, optical sources and detectors, as well as quick and practical connection methods. Today, much of Hydro One's fiber optic cable network is primarily used to transmit data that allows rapid control of the electrical transmission and distribution systems across the province. Furthermore, other companies such as Rogers Communications and Bell Canada lease some of the fiber to enhance their own voice and data networks. For transmission over long distances, optical fiber cables are installed at the very top of the same towers used to carry high-voltage electrical transmission lines. Commercial use of fiber optic technology is growing because it has advantages over other transmission systems such as microwave, coaxial cable, and wire pair. From a cost perspective, over long distances it is less expensive to transmit a given amount of data by fiber than by any other method. Fiber optic transmission is also fast in two different senses of the word. First, it can carry a large number of bits per second for a given cost. A bit is the basic unit of information used in telecommunications and is essential for the transmission of the world's rapidly increasing volume of video and other data. As is true for any system, the maximum bit rate is limited only by the frequency of the carrier wave. A key advantage of optical fiber transmission systems is that the frequency of light is far higher than in microwave or cable systems. Optical fibers are also fast in the sense of low latency. Latency means the time lag between sending and receiving for any packet of data. Since transmission distances are commonly far-reaching, if not global, lag time can become crippling. For example, telephone calls can suffer from such lengthy delays that speakers continually interrupt one another. Even much smaller delays can impede high-speed control systems, such as financial trading exchanges. Another advantage of fiber is that, unlike cable and wire pair transmission, no conductive metals are used, except where it must be armored. Fiber cables also weigh less per unit of length for a given transmission capacity, which helps keep the cost of installation as well as support structures low. Metals, on the other hand, such as copper and aluminum, are not only expensive to use, but they have also become a common target for theft. Fiber also provides a higher degree of privacy from the standpoint of eavesdropping. With fiber, no eavesdropping is possible unless direct contact is made with the fiber path. The same cannot be said for microwave transmission and other broadcast methods, which are to some extent open to eavesdropping from a distance, even from satellites. Inasmuch as it is difficult to access a signal for the purpose of eavesdropping on a fiber cable, it is equally as difficult for other signals to penetrate the cable and create levels of unwanted data known as noise and crosstalk. This inherent characteristic of fiber optic cable helps to maintain faster transmission rates over longer distances. Another way in which using fiber optic cable is beneficial is that a fiber line can easily transmit data 100 kilometers before repeater amplifiers are required to boost the signals. This long-distance capability of fiber is a major factor in keeping both cost and latency low. Despite the fact that fiber optic transmission has the advantage of being able to transmit data over long distances, locating trouble over long distances is more difficult. Consequently, knowledgeable specialists will be required to troubleshoot any associated problems that may occur during the course of transmission. In light of the fact that this technology will be here for a long time, having a thorough understanding of fiber optic transmission is an asset. Rate of transmission. Transmission of data at high speeds over long distances has always been a human problem. Even long before 490 BC, when data concerning the Persian defeat in Marathon was famously transmitted to Athens by a runner. Since then, we've transmitted data using riders on horses, beginning with the Pony Express back in 1860, by semaphore relay networks through Napoleonic times, replaced later by networks of Morse code-based telegrams, and recently radio and microwave links. Progress in transmission technology has been driven by the demand for more and faster data. Today, we want to download hours of high-definition movies in just minutes or faster. In telecommunications, an electromagnetic carrier wave that is modulated for the purpose of conveying information is transmitted through an optical fiber. Modulation of the carrier wave involves the assignment of a sequence of pulses, or a code, to convey a data stream along the optical fiber. Carrier waves with higher frequencies have shorter wavelengths, while lower frequencies have longer wavelengths. In fiber optic technology, carrier waves having higher frequencies and thus shorter wavelengths have the potential to transmit data at faster rates. However, it should be noted that it is not possible to modulate or encode a data stream faster than the carrier frequency. For example, a 1 MHz radio transmission cannot carry data faster than 1 megabit per second. In order to carry data at rates of tens of gigabits per second, carrier waves with much higher frequencies in the microwave range or higher must be used. Furthermore, since only a small proportion of the potential bit rate at a given frequency is able to be used, light having a much higher frequency in the infrared range is required for fiber optical data transmission. Although the frequency of infrared light is lower than visible light, it is still extremely high when compared to other regions of the electromagnetic spectrum. As the wavelength of light in the infrared range increases, it merges with the microwave range, and as it decreases, it merges with the visible light spectrum. Thus, infrared light is not visible to the human eye. This is because its longer wavelength prevents it from resonating enough to cause breakage of the chemical bonds responsible for turning light into nerve impulses within the eye. In much the same fashion, when infrared light is absorbed into matter, it just vibrates or spins molecules, which results in the creation of heat. This explains why infrared light is commonly used in heating lamps, as well as industrial and medical applications. Generally, it is much easier to describe regions of electromagnetic radiation in terms of their wavelength rather than in terms of their frequencies, such as thousands of gigahertz, which can become quite cumbersome. Another reason for using a wavelength-based nomenclature is that the physical size of the waves is very relevant to the engineering of their transmission. Electromagnetic waves travel at the speed of light, 3 × 10⁸ meters per second in free space, which is a vacuum, and their frequency and wavelength can be determined by the formula wavelength, or lambda, equals c, the speed of light in a vacuum, divided by f, the frequency in cycles per second. The important point here is that the 3 attributes, wavelength, speed, and frequency, are related. The longer the wavelength, the lower the frequency, and the lower the energy as well. However, as the speed changes in a medium other than a vacuum, what also changes is the wavelength and not the frequency. Suffice to say here, and in keeping with Gauss's law and Faraday's law, the frequency of the light stays constant for any given wave. In fiber optic transmission, wavelengths of infrared light are conventionally quoted as the wavelengths in a vacuum, and are normally in the range of 1 to 2 micrometers, which is roughly equivalent to 0.04 to 0.08 thousandths of an inch. Latency, dispersion, and monochromatic light. In addition to its ability to carry a larger number of bits per second for a given cost, there is another aspect of speed relative to fiber optic technology, and it's referred to as latency. Latency is the lag in real time between sending a single bit of data and receiving it. To put it in perspective, a letter sent in the regular mail via the post office will take at least a day and possibly 5 days because the carrier is paper being moved by trucks and mailmen on foot. However, by using light as a carrier, we can attain speeds close to the maximum physically possible, the speed of light. That speed is one of the fundamental physical constants of the universe. In a media other than free space, which is a vacuum, the speed of light is reduced. This means that the phase velocity, which is the time it takes the phase of any one frequency component of a wave to travel, is reduced. For example, in glass, the speed of light can be reduced by about 30%, whereas in air it is only reduced by about 0.03%. Light having a shorter wavelength travels slower through glass than light having a longer wavelength. Therefore, blue light travels slower than red, and red light travels slower than infrared. This phenomenon is called dispersion, a good example of which is a rainbow when white light is separated or dispersed into its component colors: red, orange, yellow, green, blue, and violet. For these reasons, it is better to use a single color of light when sending signals of pulsed light over long distances. If mixed colors were used, they would travel at different speeds and then become dispersed or smeared out until the original pulses merged and could not be detected. In physics, electromagnetic radiation that is of a single wavelength is called monochromatic. Fortunately, semiconductors, which are the foundation of modern electronics, can emit monochromatic infrared light having a very pure wavelength. Semiconductors include many kinds of diodes, including the light-emitting diode, commonly referred to as LED, and the diode laser that is used in fiber optic technology. In simple terms, laser diodes are complex semiconductors that convert electrical current into monochromatic infrared light. The light can be turned on and off or modulated at high speed to generate digital signals that are injected into the fiber. Similarly, semiconductors can also be used to selectively absorb or detect infrared light and produce corresponding electrical pulses. These electrical pulses subsequently become the digital data streams of our computers and communication devices. They make it possible for us to communicate with both low latency and a high transmission rate. Attenuation. Light propagates through an optical fiber with varying degrees of attenuation. Attenuation is the gradual loss of power of an optical beam and is measured in decibels per kilometer. This gradual loss is caused by several different factors, but primarily scattering and absorption by residual materials, such as metals or water ions, within the fiber core and inner cladding. Compared to other transmission media such as copper, coaxial cable, etc., attenuation is very low, giving an optical signal transmitted through fiber the ability to travel more than 100 kilometers without regeneration or amplification. In order to achieve transmission over longer distances, consideration must be given to the length of the carrier wave being used. Shorter wavelengths have the potential to transmit data at faster rates. However, in terms of range, they travel shorter distances and attenuate faster than longer waves. To optimize the range of transmission, an optical fiber is designed to function as a light pipe that guides the carrier wave between both ends of the fiber. Light is kept inside the core, causing the fiber to act as a waveguide. Refraction. Refraction arises when light passes from a medium at one speed and into another medium at a different speed. In essence, the light is propagated in a different direction or bent at the interface of the adjacent media. Depending on the refractive index of the second medium, light can bend away from the incoming light from the first medium, or alternatively, the refracted light can be redirected back toward and aligned with the incoming light from the first medium. In a fiber optical cable, a fiber typically consists of a flexible pure glass core, similar in width to a human hair, surrounded by a transparent cladding material with a lower index of refraction. If the refractive index of the cladding was higher than that of the core, light would be redirected away from the core. However, as is the case, the cladding has a lower refractive index than the core. Having a lower index of refraction means that the bent light will travel faster than the incoming light from the core. The result is just like a perfect mirror, because the bending does not, in principle, involve any absorption. Light can keep bouncing in a glancing way from one side to the other for a very long distance. This is referred to as total internal reflection. However, reflection is actually total only for light entering nearly parallel to the fiber axis. There is a critical angle which is dependent upon the ratio of light speed in the core to light speed in the cladding. If this angle is exceeded, light will leak, and this means that it cannot be used for data transmission. The speed of light in free space, which is a vacuum, is a constant and is known as the speed limit of the universe, because no matter or information can travel faster. However, when light travels through a medium other than a vacuum, it slows down, and although its frequency doesn't change, its wavelength does. The result is a change in phase velocity, which is the time it takes the phase of any one frequency component of a wave to travel. We can describe the speed at which light travels in a particular medium as a refractive index, symbolized as n. The refractive index is the ratio of the speed of light in a vacuum, or c, to the phase velocity, or v, of light in a particular medium, and is represented by the equation n equals c over v. In the light pipe model presented here, a clear glass core with a highly refractive index is surrounded by a clear glass cladding having a lower refractive index. Light entering the core nearly parallel to the axis will bounce nearly indefinitely along inside. When a transmitter light source is connected to one end and receiver detectors at both ends of the pipe, the model for high data rate fiber optic transmission is complete. Fiber quality and scattering. Several factors can cause attenuation, but it is generally categorized as either intrinsic or extrinsic. Substances inherently present in the fiber cause intrinsic attenuation, whereas external forces such as bending cause extrinsic attenuation. Intrinsic attenuation can be further characterized by two components: material absorption and Rayleigh scattering. Despite the effort made to perfect glass recipes for infrared clarity over an infrared band compatible with source and detector technology, material absorption occurs as a result of the imperfection and impurities in the glass fiber. The most common impurity is the hydroxyl or OH- molecule, which remains as a residue despite stringent manufacturing techniques. The variation of attenuation with wavelength is shown here as measured over a group of fiber optic cable material types. The three principal windows of operation include the 850 nanometer, 1310 nanometer, and 1550 nanometer wavelength bands. These correspond to wavelength regions in which attenuation is low and match to the capability of a transmitter to generate light efficiently and a receiver to carry out detection. In addition to attenuation caused by material absorption, it can also be caused by light interacting with the silica molecules in the core. Rayleigh scattering is the result of these elastic collisions between the light wave and the silica molecules in the fiber. Rayleigh scattering accounts for about 96% of attenuation in optical fiber. If the scattered light maintains an angle that supports forward travel within the core, no attenuation occurs. If the light is scattered at an angle that does not support continued forward travel, however, the light is diverted out of the core and attenuation occurs. Depending on the incident angle, some portion of the light propagates forward, and the other part deviates out of the propagation path and escapes from the fiber core. Some scattered light is reflected back toward the light source. This is a property that is used in an optical time domain reflectometer, or OTDR, to test fibers. The same principle applies to analyzing loss associated with localized events in the fiber, such as splices. Short wavelengths are scattered more than longer wavelengths. Any wavelength that is below 800 nanometers is unusable for optical communication because attenuation due to Rayleigh scattering is high. At the same time, propagation above 1700 nanometers is not possible due to high losses resulting from infrared absorption. In order to minimize extrinsic attenuation, careful attention must be paid to several aspects of the fiber itself. First, the core-to-cladding interface must be very smooth, otherwise the angle of incidence of light will exceed the critical angle and light will leak. Smoothness is not generally an issue during the manufacturing of the fiber. However, it can become an issue when it comes time to joining fibers together during installation. For this process, network technicians must use special equipment as well as a high level of skill to minimize surface irregularity at the time fibers are being connected. After the fibers are joined, the quality of the junction must be checked using an OTDR device. Second, with respect to fiber optic cable, there are two types of bending that can cause signal losses. The first is a microbend, defined as an abrupt discontinuity in the core cladding interface. These are typically caused by trauma to the fiber during the manufacturing process when the fibers are being drawn, coated, cabled, and reeled. They can also arise from trauma during the installation process, if, for example, metal clips are left on too long or tie wraps are clinched too tight and the fiber is overcompressed. The second type of bend is called a macrobend and is relatively larger than a microbend. It can occur when a technician needs to bend a cable around a corner, for example, or may need to coil some cable in a span to provide necessary slack in the event that the cable must be spliced in the future, perhaps to repair a break. In either case, a technician must consider the minimum allowable bend diameter in order to prevent both damage to the cable and loss of signal strength due to the incident angle of light exceeding the critical angle at the bend. As with splices, signal loss due to bending must be determined using an OTDR. Thirdly, both core and cladding glass must be very transparent in order to maximize the distance light travels. Although light bends at the interface, it actually penetrates about one wavelength into the glass cladding before being reflected into the axis of the core at the interface. In this way, the clarity of the cladding affects attenuation too. Types of optical fiber and dispersion. The concept of light transmission through glass fibers is actually quite old. Borescopes and surgical endoscopes made from flexible bundled optical fibers were in use long before data networks. For fiber optical data networks to become commercial, a complete set of communications elements had to be available and be reasonably priced. Optical data glass fibers have always been quite thin so that they would be flexible. However, in the early days, all the hardware just discussed was hard to build if fibers were too thin. At very small diameters, handling and exact alignment were tricky and expensive. There were also no good ways to efficiently transfer light from much larger light sources, such as light-emitting diodes or LEDs, to very small fibers, and then from small fibers to much larger detectors. For these reasons, fiber sizes became standardized at 125 micrometers outer diameter with 62.5 micrometer cores. Only rarely are 50 micrometer cores used. Cores of this size are much larger in diameter than the wavelength of the infrared light, The wavelengths of LEDs used with this large fiber is usually 0.85 micrometers, or 1.3 micrometers. As expected, the light bounces from wall to wall at glancing angles and is internally reflected by the refractive index change between core and cladding. However, the larger core size supports more than one propagation mode of light, and many possible paths down the length of the fiber are possible. Each path can cause signal distortion at the receiving end, resulting in an unclear and incomplete data transmission. This type of fiber is referred to as multimode fiber. If step-index multimode fiber is used, an initial sharp light pulse becomes distorted because not all the propagation modes are traveling at the same speed or angle to the fiber axis. Some may have a more direct path than others and may reflect more off the boundaries of the core. The arrival of different modes of the light at different times is called modal dispersion and causes pulses to spread out as they travel along the fiber. When the train of data pulses becomes so distorted that the detector electronics cannot reliably distinguish a pulse from its absence, then the fiber is being operated beyond its functional distance and is useless. The bigger the fiber diameter relative to the wavelength, the more possible range of reflection modes and the more limited the range. The other way to look at this is that for any fixed distance, the bandwidth is limited by dispersion. If the pulses are too close together, as is needed for faster data traffic, they also smear together earlier. Modal dispersion can be partly overcome by use of graded index multimode fiber. In this design, the core's refractive index decreases gradually away from its center, finally dropping to the same value as the cladding at its edge. This greatly decreases modal dispersion because refraction bends the light rays back into the fiber axis before they reach the cladding boundary. It offers hundreds of times more bandwidth than step-index multimode fiber, up to about 2 GHz over 1 kilometer. Almost all multimode fiber is now graded index multimode fiber, rather than the original step-index multimode fiber. Advances in semiconductors, lasers, as well as improvements to detectors and connectors have now made it possible to reduce core diameter until it approaches the wavelength of the infrared light. These can have intense, very narrow, very monochromatic beams at the most useful wavelength between 1 and 2 micrometers. A 9-micrometer core has become the new standard. However, the cladding diameter remains 125 micrometers. Having a core size of only 9 micrometers limits the core to being able to propagate only a single mode parallel to the core axis. Fibers that support a single mode are called single-mode fibers. Despite the fact that it may take hundreds of meters to settle into one mode, eventually only a single path exists without any bouncing, even if the fiber has mild curves. This significantly reduces attenuation and almost eliminates modal dispersion. In this way, the fiber acts as a waveguide that can transmit light over longer distances. As a bonus, the use of lasers reduces another form of dispersion called chromatic dispersion. Chromatic dispersion arises from the mixture of light wavelengths traveling at different speeds. Also, laser sources are narrow in spectral distribution compared to LEDs, so they smear much less over distance. As a result, multimode fiber is used for short-distance communication links, such as those commonly found in interior networks between buildings and within buildings. Single-mode fibers are used exclusively for long-distance runs longer than 1,050 meters, or 3,440 feet, such as between cities. Single-mode fiber does not have more stringent hardware requirements, making it a little more expensive, but it is capable of far longer runs without repeater stations. Note that you cannot make simple connections between different fiber types. light going from multimode to single mode will encounter a huge core diameter mismatch. In that direction, it will cause loss of 20 decibels or 99% of the power. However, it is true that going from a smaller fiber to a larger fiber will cause no unusual loss for light going in that one direction. Advantages of using Otdr. When characterizing fiber in an optical network, the optical time domain reflectometer, abbreviated Otdr, is commonly used to determine the location of any fiber optic breaks or splices. It is one of several tools used to troubleshoot the quality of fiber optic transmission cables and to find the locations of any needed repairs. The acronym Otdr contains the word optical in its name to distinguish it from other instruments that are used in a similar way to diagnose problems in cable transmission. The words time domain reflectometer denote that all information is obtained from the amplitude of a light pulse that is reflected back versus the time from when the original pulse was sent. Since the speed of light traveling within the fiber is known, the time it takes to travel can accurately be converted to a measure of distance. The concept of putting a source of known power at one end of the line and measuring the power at the receiving end with a meter is not new. An OLTS, or optical loss test set, is a highly accurate tool that determines the total amount of power loss or attenuation in a fiber span under test. At one end of the fiber, a stable light source emits a signal that consists of a continuous wave at a specific wavelength. At the other end, an optical power meter, or OPM, detects and measures the power level of that signal. To obtain accurate results, the power meter must be calibrated for the same wavelength as the incoming signal. In very general terms, the difference in power level of the signal measured at the transmitting and receiving ends corresponds to the loss of the fiber under test. An OLTS requires there be a technician at each end of the fiber, and although it will provide very accurate loss results over the entire span, it will not identify and specifically locate connection points or nodes in the span of fiber. Alternatively, an Otdr is an instrument that was built to chart power loss against distance between nodes along the span of fiber tested. For many problems, it can be used with access to only one end of the fiber. For fibers that might run more than 100 kilometers to the next access point, this is clearly a big advantage. Otdrs do have limitations when used for short distances, and they also have inherent problems measuring the size of some types of line losses, unless you can measure from both ends of that line. Principles of operation. The basic aspects of the operation of an Otdr are common to all makes of the instrument, and these include light generation, light detection, connection to fiber line, and display. An Otdr is much like a radar looking through a fog along a single fixed path. It sends out a pulse of infrared light and displays the echoes that return over time. The echoes that are returned are measured and integrated as a function of time and are called events. Each event marks the location of a fusion junction, a connector, terminations, and other features of the line. Because we can obtain an accurate speed of light in the fiber from manufacturer's data, the instrument can substitute an accurate distance for time to each of these events. This helps physically locate them if repair is needed. As might be expected, many echoes arise from different types of defects that generate reflections. For example, a badly aligned fuse joint connecting two fiber lengths. Another example would be a free end of fiber from a break or a termination. However, not all defects cause reflections. A common example is an excessively tight bend, called a macro bend, somewhere along the fiber. There are also microbends, which are flaws in the smoothness of the core-to-cladding interface. Both cause partial failure of internal reflectance, and hence leakage of light, but no reflections. But an OTDR can see these events too because of Rayleigh scattering. Even totally pure glass has random density variations at molecular size scales. Although these are much smaller than the wavelengths of light, they do, although weakly, scatter that light in all directions. It is Rayleigh scattering that causes the view down the fiber to be like looking into fog. Because of Rayleigh scattering, the fiber weakly echoes the outgoing light pulse everywhere along its length. Later backscatter is attenuated more and more according to its distance, usually smoothly and proportionally. When an outgoing light pulse encounters an absorptive effect, the brightness of the Rayleigh scattering beyond the defect will be weaker than expected. This causes a change in the slope of the light returning over time to the OTDR. That abrupt drop in backscattered brightness lets us accurately locate non-reflective defects like excessively tight bends. The laser. All OTDRs use powerful infrared laser light source systems that can be pulsed rapidly and repeatedly and come equipped with the capability of setting the pulse duration. The pulse width is actually the time during which the laser is on, and since time can be converted into distance, the duration of the pulse has a length. The energy of the light in the pulse is what creates the back reflection necessary to characterize the fiber. A shorter pulse carries less energy and therefore travels a shorter distance along the fiber. It loses energy faster because of attenuation, connectors, splices, etc. If the pulse is too short, it will eventually diminish and become indistinguishable along the noise floor level, never reaching the end of the fiber. A long pulse carries much more energy for use in extremely long fibers. However, since longer pulses have more energy, the width of the dead zone following an event will be wider. Pulse width is also a significant factor when it comes to an instrument's sampling resolution. Sampling resolution is defined as the minimum distance between two consecutive sampling points acquired by the instrument. There must be a high number of sampling points taken during characterization to maintain the best possible resolution. Depending on the selected pulse width and distance range, this crucial parameter could vary from 4 centimeters up to a few meters. Some OTDRs also allow the user to control the intensity of the pulse. Some models can be operated at a variety of wavelengths, either to match those used in multimode fiber or the longer wavelengths used in single mode. The appropriate wavelength could also be selected when working on live fiber in order to minimize interference with the data stream. OTDRs use lasers as light sources and are best used with single-mode fiber for troubleshooting long fiber runs. When it comes to multimode fiber, it's possible to use an OTDR to troubleshoot. However, caution must be exercised since there are some extra problems to watch out for in addition to the usual problems relative to shorter distances. In some types of systems, multimode fiber is laser-driven, but usually for low-bandwidth, short-distance systems, LEDs are used and are also less expensive. Troubleshooting an LED-driven multimode fiber with a laser-driven OTDR may cause misleading results. A laser's narrow, highly collimated beam will take a path on average closer to the axis of the core than an LED beam would. The result is that attenuation is understated and several types of events are more difficult to characterize. For example, poorly aligned fusion splices. These powerful lasers must also be able to be pulsed for very short intervals. A pulse of light occupies a specific length of fiber as it travels, and since there are technical limits to how short the pulse can be, the distance resolving ability of the instrument is also limited. Adjacent events separated by less than the distance of the pulse length cannot be distinguished from a single event. The reflection will appear smeared together and blurred. The longer the pulse, the more difficult it is to distinguish between events. For example, if a fiber core has a refractive index of 1.4, meaning speed of light is 71% of vacuum speed c, and the laser pulse is effectively 20 nanoseconds long, we can calculate that the pulse occupies 8.4 meters of fiber as it travels. Two defects within that distance of each other can only show as a single event. In summary, short pulses are desirable for a sharper view. However, there are limits to how short the pulse can be, which in turn limits the distance resolving power of an OTDR. It is one reason that OTDRs are difficult to use for characterizing fiber over very short distances, such as within cable racks or within offices. The detector. The components of a detector include a sensor and amplifiers, and as a system, it is characterized by its dynamic range. The dynamic range is the difference between the highest and lowest amplitude, a measure of the amount of light that the detector can represent data for. The bottom end of the dynamic range is called the noise floor. Noise is created by small, fundamentally random signals in the detector electronics and is very similar to the familiar hiss that's heard when the volume is turned up on audio amplifiers with no input. At the lower end of the dynamic range, a very weak light pulse of reflected light will get mixed in with the noise and render the response no longer proportional to the light's power. At even lower light powers, all that can actually be reported is noise, and the resulting trace looks like a series of random, jagged peaks. At the higher end of the dynamic range, a very strong light pulse of reflected light that is stronger than the system's limit will not be entirely represented. In this case, the detector has been overloaded, and the event signal peak will appear clipped at the top. The detector can also become overloaded right after a highly reflective event when, depending on the pulse width, it needs a period of time to recover before being able to detect another event. The time it takes to recover is referred to as a dead zone, since time represents a distance or zone along the fiber. When setting the pulse width, it should be kept in mind that longer pulses will increase the length of a dead zone. Being nearest to the instrument, the biggest reflection and the longest dead zone will probably result from the connection of the fiber cable to the OTDR. Even when set to the minimum pulse width, the instrument may be blind for the first 50 meters as the sensitive detector recovers from the strong reflection. In order to avoid possibly missing an event that could occur during the time it takes for the detector to recover, a long launch cable should be connected to the OTDR first. Adding the cable adds distance away from the instrument, so that the connection to the fiber being tested at the opposite or far end of the launch cable will reflect less and thus have a smaller dead zone associated with it. The launch cable must be tested in advance of being used for this purpose, only to ensure that any unexpected events don't appear on the trace. A length of between 70 and 200 meters is often recommended. Because of the limits to detector system performance, very strong reflections can cause dead zones, clipping, and ghosts, all of which can make accurate measurements difficult or just cause confusion. These strong reflections usually arise because of air gaps between the ends of the fiber being tested and the connectors that are joined. To reduce the amount of reflection at these locations, one of the simplest and quickest solutions is to temporarily fill the air gap with a fluid having a better match to the fiber's refractive index. Specialty index matching gels are available for this purpose. However, if at a critical point in time they are not available, petroleum jelly or silicone high vacuum grease can be substituted. Note that water or water-containing fluids must be avoided because of the broad infrared absorption of water. Regardless of what type of gel or fluid is used to fill the air gap, it must be thoroughly removed from the temporary junction. Any residual liquid will tend to accumulate dust over time, which can have disastrous results for transmission in that fiber line. Also note that refractive index matching gel should never be used with the connector on the Otdr because of the problems associated with cleaning and its affinity for attracting dirt. Instead, use a launch cable with a high-quality connection to the Otdr and use the gel at the far end of the leader cable if necessary. The viewing system. Like its other components, the proper way to use the viewing system of an Otdr follows from its limitations. Due to the relatively limited size of the viewing screen, accurate measurements cannot be expected unless selected events are viewed with enough magnification. It may be satisfactory to start with an overview of the entire trace, but then it will be necessary to reduce the distance base and scroll to the events you wish to analyze. Then, the gain can be adjusted so that the event occupies a large part of the screen vertically as well as horizontally. With the event adequately magnified, you can then examine for clipping, tailing, and noise and set your measurement cursors accordingly. Remember that no amount of time-based magnification can help resolve events blurred by too long a pulse width. You must go to shorter pulses and probably average longer to reduce noise while improving resolution. Implicitly, the Otdr shows a trace of returned light against a timeline, but usually what you need is distance so that you can determine where a defect is located. Sometimes you only need an approximate distance because you know where the connectors are located, for example. But in other cases, you might need a very exact location. Two factors must be entered into the Otdr setup for time to be converted exactly to distance. The first is the refractive index of the fiber core. The larger this refractive index, the slower the speed of light will travel through the fiber. The refractive index at each wavelength will be found in the fiber manufacturer's data. The second factor is the helix factor. Fibers in a multiple fiber cable are helically stranded around a central strength member core, usually referred to by its DuPont trade name as Kevlar, and consequently around the axis of the resulting cable. Each of the fibers and the central core are all surrounded by a plastic jacket. The term lay length is applied to describe the length along the cable it takes for one fiber to go all the way around a cable, from the top, around to the bottom, and back up to the top. There are distinct advantages to helically stranded cable over non-stranded or straight lay cable, particularly in the construction of fiber optic cable. Glass fibers are sensitive to bending that can cause loss or attenuation. If there is an excessive number of microbends, system performance can be prohibited. Also, bends place the outer surface of the glass fibers under stress, leading to the growth of microcracks and can eventually cause fiber breakage. Helical stranding in a fiber optic cable reduces these types of stresses that the fibers may be subject to during or after installation. In a non-stranded or straight-lay cable, each cable element essentially stands alone and is unable to offer any resistance to bending. Due to the helical arrangement, fibers within a cable are spiraling around the cable core that results in the glass fibers being about 1% longer than the cable itself. By adjusting the helix factor on the Otdr instrument, the length of the Otdr distance axis is always equivalent to the physical length of the cable and not the fiber. If the fiber is, for example, 1.15% longer than the cable, then increase the refractive index entry on the Otdr by that amount, by multiplying Ri by 1.0115. This will account for the apparent slowing of the light in the cable, caused by it traveling farther in the fiber. The helix correction factor can be adjusted in accordance with the manufacturer's instructions, outlined in the user's manual, depending on the model of Otdr being used. Cable lengths are stated on reels of cable, so you can adjust the refractive index input to your Otdr until it measures a length equal to the known length of cable. The recording system. Otdr displays also have recording functions. Two recorded traces can be presented at the same time as an overlay for easiest comparison. Stored traces allow later comparison of the same line in order to see at a glance what was changed. It's also possible to overlay traces taken with pulses sent using different wavelengths. Longer wavelengths are more sensitive to stressed glass in the fiber, so wavelength comparison helps find pinch points or excessively tight bends in an installation. By comparing trace overlays taken with different pulse widths, it's possible to choose the best compromise between noise and resolution for a particular event. This may be necessary when searching for events lost because of the poor resolution of long pulse pulses. In the overlay, you can see both near events at short pulse widths best for resolution, and far events at the necessarily longer pulses needed to limit noise. Another important use for a stored file is to transmit it to another Otdr worker at the other end of the same line, for averaging with a trace done from that end. Many Otdrs have a software routine specifically set up to do this bidirectional combination. Bidirectional averaging is absolutely necessary to eliminate errors in splice loss measurements. Visual fault locators. When attempting to diagnose problems on short lines or problems very near to the Otdr itself, a number of techniques are needed, such as minimum pulse lengths, launch cables, and the ability to identify ghost reflections. If closer than the minimum Otdr pulse length, it may be completely impossible to use an Otdr. Nevertheless, another technique is possible. Leakage of light accompanies most types of defect in a fiber line. As a result, it may be possible to visually spot the leak location by connecting the line to a visible light source. Many Otdrs now come with visible light sources built in, usually red lasers for best range. They are called Visual Light Fault Locators, abbreviated VFLs. They're not technically a part of the Otdr system, but sometimes are included in the same instrument box for convenience. There are also separate devices the size of a small flashlight with a connector for a fiber cable. A visual fault locator cannot provide numbers on how bad a leak is, but it can work well for the near range when Otdrs become difficult or even impossible. VFL use depends on how much you can reduce ambient light, how bad the fiber leak is, and the opacity of the cable jacket or connector where the leak occurs. Yellow and orange jackets will be the most transparent to the red light. Gray or black jackets or multi-fiber cables will probably not be transparent enough. Obviously, visual access to all the suspect length of fiber will be required. VFLs can also be used for finding cable breaks, macro-bending losses caused by kinks in the fiber, bad patch cords, and bad splices. A mechanical splice can be optimized visually by adjusting the positioning or rotation of fiber in the connector until leaked light is at a minimum. VFLs are helpful for quick checks on fiber continuity up to a few kilometers, such as a check of a reel of fiber that might be suspected of damage. They can also be used to trace a specific fiber in a multi-fiber cable. Maximum range is limited to 3 to 5 kilometers due to the poor transparency of fiber at visible wavelengths. Principles of analysis. The Otdr software displays obvious faults and connections on a generated graph, known as a trace, calibrated to indicate signal strength in dB in the vertical axis, and distance in miles or kilometers in the horizontal scale. The visual plot of a fiber's backscatter reflection pattern is called a signature. The optical attenuation or power loss at each event and that of the overall fiber under test can also be easily observed in the Otdr signature. The height of the trace at any point represents the quantity of backscattered light and corresponds to a distance along the fiber. The returned light power is expressed as a fraction of the outgoing power, but because the ratios are large, the common logarithm of the ratio is used and further multiplied by 10 to give decibels. We estimate the size of the drop in returned light caused by the event based on intensity of backscatter before the event versus after the event. In fact, we subtract the after intensity from the before intensity and call that the event loss. All modern OTDRs have an automatic mode capable of analyzing the signature on a trace and producing a list of all the events on a fiber, together with their magnitudes in dB and their locations in meters. Automatic mode can be a time saver, and its results may even be satisfactory for some purposes some of the time. However, despite the fact that instrument manufacturers keep building better automatic event recognition, the software is often a poor substitute for an operator's trained judgment. There is an aspect relevant to the concept of dead zones that is related to how humans can't see in the dark immediately after a bright flash of light. In a very similar way, OTDR detector systems require a pause to recover after a very strong signal has been detected. During the pause, however, light still travels through the fiber but cannot be measured until the detector has recovered. An event dead zone refers to the minimum distance after a reflective event that the detector can recover and detect another event without the events being merged together and the loss of the consecutive event unable to be measured. Usually, the dead zone is specified by the manufacturer of the OTDR after having established it using the shortest available pulse width to minimize the zone and allow the detection of closely spaced events. An attenuation dead zone refers to the minimum distance after a reflective event that the detector can accurately measure the loss of a consecutive event. Both types of dead zones originate from strong Fresnel reflections, which are reflections that can be predicted by equations that describe the behavior of light between media of differing refractive indexes. For example, Fresnel reflection occurs at the air glass interfaces at entrance and exit ends of an optical fiber. After large reflective events, the late stages of the dead zone may show a small bump or even a small valley, then a bump, before the true baseline appears. These are artifacts of the electronics. Basically, the analog-to-digital converter system is slow to track large, fast events and can overshoot. If you need to check whether such features are real or artifacts of the instrument, use a long launch cable or in some other way reduce the magnitude of the reflection. Even if a reflection does not overload the electronics so as to cause clipping, there is usually a significant dead zone following any peak. With small peaks, the length of this zone may be insignificant or shorter than the resolution allowed by the pulse length. The reflection itself, from the end of a fiber for example, usually has no physical length of its own. For essentially point source reflections, overall width of a reflective peak depends on the outgoing pulse width. The leading and trailing edges of a peak have shapes that depend mainly on the fidelity of the detector electronics. The leading edge is usually much sharper and shorter than the trailing edge. However, the key point is that within both leading and trailing zones, other events in the light signal cannot accurately be measured. One way to improve event detection and measurement, particularly where the signal is weak, is to set the instrument to repeat the pulse a number of times and let it average the return traces. The noise that arises in the sensing system is random, so it tends to average to 0 at large numbers of repetitions. Over many repetitions, the true signal keeps adding up and eventually becomes visible. When studying closely spaced events, the averaging number also improves spatial resolution because it helps to reduce noise during high bandwidth analysis. Averaging is determined by the OTDR's sampling points and the acquisition time for the measurement. The ratio of signal to noise, or SNR, tends to improve in proportion to the square root of the number of traces that are averaged. Averaging 4,000 pulses gives twice the improvement of averaging 200 pulses. As signal becomes weaker and more deeply buried in noise, it can take a rapidly increasing number of pulse repetitions to get any useful data. It is a case of diminishing returns. If a few minutes averaging doesn't clear up noise problems, you will have to try something else. OTDRs have a free run setting that presents the average trace as it accumulates. This lets you watch the noise clear away as number of pulse repetitions builds up. Free run gives you a quicker sense of whether you need to compromise and set pulse width longer, or whether with patience you will see clearly to the distance needed at the resolution needed. At some point, signal averaging may take so long that it may be quicker to pack your instruments in the car and travel to the other end to make your measurements. Bidirectional analysis. There are two basic reasons why OTDR traces need human interpretation. First, sometimes a trace is too muddled to sort out automatically. Second, very often there are events that software cannot interpret correctly because of the basic physics of fiber optics. For example, events that are very close in proximity may be difficult for software to sort out, especially if baseline backscatter is uncertain because of noise, or if the pulse length used is similar in length to how far the events are separated, or if highly reflective events have caused peak tailing that overlaps with subsequent events. In these situations, measurement cursors should be adjusted manually based on human judgment. For example, pulse length or pulse wavelength may need to be adjusted in multiple runs in order to untangle some mixed events. A second kind of event that an OTDR can misinterpret is a break in the continuity of a line from a bad connector or an outright fracture. Usually, these show as strong back reflections, and an auto-analysis will identify those cases. However, it is possible that the OTDR can be fooled by non-reflective breaks. These can occur if the fiber is pulverized, so that it has few facets properly angled to backscatter and instead just leaks light. Non-reflective breaks can also arise from a fiber break immersed in any liquid approximately matching the refractive index of the core. If a trace abruptly goes to noise at a distance where the instrument would normally show a reasonably noise-free backscatter signal, a non-reflective break should be suspected. A third kind of event is fusion splices. These always require operator involvement if accurate measurements of their quality are needed. A good fusion splice may cause no reflection and so little loss that it is difficult to see against background noise. There may be no satisfactory setting of the auto-recognition threshold in this case. The technician may have the advantage over the OTDR in knowing where the splice should be from other data such as system schematics, and so can spot the weak event amid the noise. Some effort adjusting pulse width settings, pulse averaging, or even wavelength may reduce noise in that area, even at the expense of other areas, and could result in a measurement that the auto mode setting could not match. Conversely, it is entirely possible for a bad fusion splice to also show 0 dB loss. Actually, a fusion splice can show any of the following: lower than true loss, a correct loss, or greater than true loss. This is one of the basic limitations on OTDR use that must be recognized. Simply put, an OTDR used from only one end of the line cannot tell you anything about a splice loss except the splice location. In the case of an apparent 0 dB event, even seeing the location will be impossible. Ghosting. When there are two or more highly reflective locations in a fiber line, nothing prevents the light pulse from an OTDR from bouncing multiple times between those reflective locations. Normally, such multiple reflections are weak enough that they can't be seen against the background of other light arriving at the detector at the same time. But this is not always so, especially if a short cable with highly reflective connectors is being tested. Visible peaks caused by multiple reflections are called ghosts and are caused by the reflected light from the far-end connector reflecting back and forth in the fiber until it is attenuated to the noise level. The near-end reflector may be the connector of the OTDR to cable, for example, which sends enough reflection back down the line again, almost like the OTDR's original pulse. This repeated reflection makes a visible echo appear at twice the distance of the primary reflection from the OTDR. If there is a reflective event in the trace at a point where there is not supposed to be any connection, and the connection from the launch cable to the fiber being tested is highly reflective, ghost reflections may appear at multiples of the length of the launch cable or the first cable being tested. They seem like real reflective events, however, they will not show any loss. In order to help sort out real events on a trace, it is extremely useful to know the actual lengths between components, such as connectors. If possible, check the plant drawings for the line to be examined. Also, using a launch cable of known length and knowing the approximate length of the cable or cables under test will help isolate ghosts and prevent them from confusing the actual test data. Gainers. If the OTDR pulse passes from fiber having higher backscatter through a splice to fiber having lower backscatter, then an exaggerated loss will be seen at the splice. This might easily seem a routine bad splice to an untrained OTDR operator and not be remarkable. However, if the order of travel is reversed so that higher backscatter follows lower backscatter, then what is termed a gainer will appear. The trace will jump up at the splice to a new higher baseline. This is likely to be considered as very odd. However, since only a tiny part of the outgoing light pulse is backscattered anywhere along the fiber, some fibers will backscatter a bit more than others. Measuring with the OTDR in both directions and averaging the losses can overcome these variations in a backscatter. A gainer seen from one direction is an exaggerated loss seen from the other direction. The errors in each direction cancel out, and the average value is close to the true value of the splice or connector loss. Understanding the limitations of the OTDR is paramount before interpreting a fiber trace. The process of measuring from both directions is called bidirectional analysis and is a standard requirement for splice quality control. Obviously, since the other end of a fiber could be as far as 150 kilometers away, it may be difficult to obtain access. One solution may be to have the measurement done by another person at the other end, also equipped with their own OTDR. They then send you their trace by email, and you combine it with your own trace using software included in the instrument for this purpose. Alternatively, they could phone you over their events list with their apparent magnitudes, and you manually average their list with your list, event location by event location. It takes some coordinated effort to do bidirectional testing on long fibers, but there is no other way. The need is inherent in the physics of fibers, and so far there is no automated software to arrange measurements at both ends without your involvement. It should be noted here that the physical principles that justify bidirectional OTDR averaging on single-mode fiber do not apply to multi-mode fibers. Building and campus cabling are usually multi-mode fiber, using light-emitting diode sources for low and medium-speed networks. However, when laser is used in order to achieve high enough backscatter, the OTDR has problems. Laser light is transmitted by multimode fiber only in the center of the core because its emission angle is so low. It is false to assume that the real loss of a splice between two fibers is the same for both propagation directions. In fact, transmission from an initial fiber to a larger one is likely to experience very low loss, while the transmission from a large fiber to a smaller one will experience very large loss. Another important point is that the true insertion loss between two fibers does not solely depend on the fibers themselves, but also on the actual mode distribution of light within the launch fibers. Although the impact of backscatter differences between two multimode fibers is removed by performing bidirectional analysis, the final result does not give the true loss of the splice as opposed to single-mode fibers. Least square analysis. The Otdr measures distance and loss between two events, but calculates the best fit line between the 2 points using the least squares method to reduce noise, often abbreviated as LSA. This can be useful if you're trying to estimate the slope and offset of a section of a trace that you know ought to be straight if it weren't for noise. The Otdr software computes a best fit line through the noise, taking into account all the measurement points between the two that you select for beginning and end of your section. As a result, the fitted line usually won't pass exactly through your chosen points. The strength of this method is that the best fit line does not depend very strongly on the particular endpoints you choose. Still, it is a judgment call where to put your endpoints. More spread between them will base your best fit line on more points in between, which is usually good. But including any features in the span that aren't truly part of a straight line is going to contribute inaccuracy to the best fit line. You can fit a line to data that isn't at all a straight line, like the trailing edge of a large reflective peak, but the line won't be useful for anything. Section attenuation. The total attenuation of a section of fiber in decibels per kilometer can be obtained manually by simply setting cursors at beginning and end of the desired location. When you pick the points, the instrument will then compute the difference in backscattered power between the 2 points and divide by the difference in distances. This is called two-point section attenuation. It could be used to check whether a fiber meets the specific attenuation rate. If various events happen to be included in the section between the 2 points, the attenuation rate will be the average over that combination of length and events. Careful consideration should be given to choosing the points in accordance with what needs to be known. If checking to see if the fiber meets specifications on its fundamental attenuation rate, select the longest and straightest section possible, and avoid setting your cursors in regions that might be curved, for example, near splice or connector events. Be sure to magnify both distance and power scales so that the desired section fills most of the display. The problem with a two-point section attenuation is that noise may cause the trace to be ragged, so that one or both points chosen could be poor representatives of the line. Rather than try to visually estimate where in the noise to choose the points, use the least squares analysis function of the Otdr. In this way, just the endpoints of the segment are being manually selected. The software chooses the best fit line for all the points in between and reports the slope in decibels per kilometer. Again, zoom in the display and set the cursors to bracket the longest straight section available so that you base your fitted line on the maximum number of available scan points. For comparison to specifications, a standard method is required. The result depends on the user entering a correct source wavelength, pulse direction, and fiber length test range into the Otdr. In addition, the effective group refractive index is required so that accurate distances can be derived from times. The group refractive index is provided by fiber manufacturers, or is measured using EIA-TIA-455-60. The standard method for measuring attenuation of an installed optical fiber using an Otdr is EIA-TIA-455-61. 4-point event loss. Most often, it is not the slope of the attenuation line that is of interest. It is the loss caused by an event on that fiber. To get an estimate of the loss caused by a particular event, 4 points are required. The line before the event should be extrapolated forward, and the line after the event should be extrapolated backward so that both lines pass the event. The difference in the heights of these lines right at the event is the loss caused by the event itself. A beginner might do this the wrong way and subtract the height of a point just before the event from a point just after the event, a sort of 2-point measurement. It would be in error because the heights are not being compared at the same distance. There is fiber between the 2 points. The loss in the fiber spanning the event is added to the event loss, making it too large. The longer the pulse width, the longer this span will become. In multimode fiber, with its much higher attenuation, the error can be a larger problem. Also, in some cases, the loss might be preceded by a strong reflective peak with a long tail. Avoiding the tail will exaggerate the span between your 2 points. As usual, you can use the instrument software in a partially automatic mode using least squares analysis. If you have chosen the 4 points, the software can least squares fit the segment between the leading points pair, and separately least squares fit the segment between the trailing points pair. It will then automatically subtract the heights of those 2 lines at the event location. This is good use of the automated functions because you get to use your intelligence to choose the best locations of the 4 points, and the software does the tedious calculation for best fit lines and differences. Reflectance measurements. Optical return loss. The reflectance of an event, or its optical return loss, or ORL, is measured as the ratio of the incident pulse divided by the reflected pulse and is expressed in decibels. Incident power is always enormously larger than reflected power, so the ratio is a large number. However, it has long been common to arbitrarily assign a negative sign to the reflectance in dB. You will see this on instruments and in much of the literature. It amounts to using the reciprocal of the ratio. To use our example again, a reflectance of -40 dB just means 1/10,000th of the incident power has been reflected. Reflectance measurements with an Otdr are characteristically high in measurement uncertainty because of the low power of the reflections. There is also the uncertainty in what to assign as incident power at the reflection, which might be far down the line. Incident power has to be estimated from the backscatter level just before the reflection. A source and meter set may be preferable if more exact values are required. Unfortunately, this would require access to both ends of the fiber line, and it still won't give the location of the event. So the Otdr may have an advantage if you can live with the approximation. 2-point reflectance measurement. For the first cursor, select a location on the early side of the peak, where the backscatter is still at baseline but as near as possible to the peak. For the second cursor, select the top of the peak. The instrument will estimate the power of the reflection. Introduction to safety hazards. This unit covers some of the known hazards in working with fiber optics installation and in working with the instruments used to troubleshoot those installations. Mostly, the hazards are the usual ones on any hydro site. Fiber cables are carried on the same towers as used for high-voltage power transmission. Although fiber cables used in these applications are themselves non-conductive, at least 5 installers have been killed in recent years in the United States. In every case, the cause was related to poor planning when working in a high-voltage power environment. In addition to high voltages in the work area, there are common fall hazards. Always be aware and focus while climbing a tower or even working on a ladder while working a cable run in an office ceiling. Just falling a short distance can cause a serious injury. Plan your work and don't take risks because of lateness or because of the pressure associated with the type of work being performed. Be sure the basic rules are posted where all will see them, and review with new personnel or those that might need a refresher. Eye protection. Eye protection with side shields should be worn at all times in a work area. There are special eye protectors for working with laser sources. Safety glasses provide a shield from splashed solvents or adhesives, from molten metal spattered by arcs, from tiny flying shards of wire or glass, from lash of wire or cable, as well as from other unanticipated incidents. Safety glasses will also prevent you from touching your eyes with contaminated hands in a distracted moment. Even when leaving a work area temporarily, be aware of possible hand contamination, such as stray glass shards after cutting fiber. Always wash your hands before making any contact with your eyes or with your contact lenses. Fiber hazards. Bare fiber ends are very stiff, brittle, and only 125 micrometers diameter. The end of a fiber can penetrate human skin much like a needle and then break off easily. Slivers are very difficult to see and remove without further fragmentation. They can fester painfully in your hands for weeks until your body gets them out. In other locations, they can be more serious. Fiber scraps are generated by stripping or cleaving during the process of cable preparation. Some of the particles are difficult to see with the naked eye, and so the standard procedure is to work on a dark surface. Double-sided sticky tape may also help to temporarily immobilize particulate scrap. As much as possible, prohibit fiber shards from getting on the floor where they can be spread by shoes. Use outer work clothes that can be segregated from home clothes, and use a disposable apron if available. Budget enough time to be systematic in cleaning up. Use a dedicated container for disposal of shards and any other sharps. Mark it so that no one can mistake it for any other purpose. Avoid bringing food or drink or smoking supplies in close proximity of your work area. Developing correct safety habits will help to prevent the possibility of a serious accident from occurring. Fiber safety kits are available and contain FS100 Polishing Work Mat. A black vinyl mat helps you to easily see the fiber scraps. It can also serve as a subsurface for some polishing applications. Being resilient, the mat helps you to quickly pick up the fibers. It can also provide better polishing results. FS200 Fiber Scraps Trash Can. A disposable fiber scraps trash can. FS300 Safety Glasses. Have a single lens wraparound feature to be worn over prescription glasses. FS400 Bifurcated Cleaning Swipes. These two-pronged swipes put an end to spillable bottles of alcohol and messy hand wipes when cleaning fiber ends before splicing, cleaving, or terminating fiber. The tube contains 99% isopropyl alcohol. Hand pressure breaks the seal, and the alcohol is dispensed only when you squeeze the tube, reducing evaporation and alcohol waste. 10 swipes per package. Remember that isopropyl alcohol is moderately flammable. FS500 Splinter Removal Tweezers. These have a Teflon coating to cushion the gripping tips so that you have a better chance of pulling glass fiber splinters out of your hide without further fragmenting the glass. Solvents. Depending on the circumstances, a variety of solvents may be used when working with fiber optic cable. Prior to use, read the Material Data Safety Sheets or MSDS to understand the hazards that are specific to a particular solvent. It is best practice to work with the smallest container practical while at your workstation in order to minimize a possible spill. Most of the solvents used will have low boiling points and will evaporate very quickly. This means that they easily become available for breathing in, and since most are toxic to some degree, having good ventilation is particularly important. Many solvents can also be absorbed significantly through the skin, depending on the length of time in direct contact and the surface area covered. To prevent a serious injury, remove any contaminated article away from the skin as soon as possible. Once removed, immediately wash the affected area thoroughly. Don't wait until you feel tingling or burning. By then, the solvent is doing damage, and it has soaked in and it won't stop immediately when you wash. When using a solvent for cleaning purposes, such as isopropanol, be aware that many are, unfortunately, quite flammable. Before opening a container of any flammable solvent, be mindful of any potential ignition sources in the immediate vicinity. These sources may include items such as fusion splicers, powerful laser-containing devices such as Otdrs and OLTSs, some kinds of motors, and ordinary 120-volt power switches. If solvents are being used, ensure that there is a fire extinguisher of the proper type in the immediate vicinity. In summary, here are 10 general fiber optic work safety rules. 1. Keep all food and beverages out of the work area. 2. Wear disposable aprons to minimize fiber particles on your clothing. Use protective gloves. Treat fiber optic splinters the same as you would glass splinters. 3. Always wear safety glasses with side shields. 4. Never look directly into the end of fiber cables until you are positive that there is no light source at the other end. Use a fiber optic power meter to make certain the fiber is dark. When using an optical tracer or continuity checker, look at the fiber from an angle at least 6 inches away from your eye to determine if the visible light is present. 5. Only work in well-ventilated areas. 6. Do not touch your eyes after working with fiber optic systems until hands have been thoroughly washed. Contact lens wearers must not handle their lenses until they have thoroughly washed. 7. Keep all combustible materials a safe distance from the curing ovens and other ignition sources. 8. Thoroughly clean your work area when you are done. Dispose of cut fiber pieces in a marked, dedicated container. 9. Do not smoke anywhere near fiber optic systems. 10. Don't do cutting, joining, or cleaning work on live fiber. Laser hazards. As a matter of hydro policy, approved laser glasses shall be worn when any fiber optic cable connected to power equipment or a patch panel is not terminated, when work takes place in front of a fiber patch panel with uncapped connectors, when splicing a broken fiber optical cable, when cleaning a fiber connector. That doesn't leave much you can do around a fiber terminal without those glasses, so just assume you need to wear them all the time. Let's consider the reasons they're needed. Hazards of laser light through fibers. The infrared light hazard from laser-driven fibers is different in character from laser sources. The power is similar but only remains concentrated to a dangerous degree right at the free end of fiber. When the beam comes out of a fiber, it spreads in a cone with a minimum apex angle somewhere in the 10° to 40° range, as determined by the fiber design, its numerical aperture, and increased further by any defects in the end shape. After only a few tens of centimeters, it has insufficient power density to be hazardous. There is a notable exception. Although your eye can't by itself focus such a divergent beam, any device with a strong enough convergent lens can still concentrate the beam back to dangerous intensity. Now, fiber is all around you in a typical installation, and you will often be in the middle of many free ends. It is not always obvious where a break or a loose connector has left a free end. You cannot tell by looking whether a free end is live and emitting. Your safety depends on not getting your eyes, or your skin for that matter, too close to any fiber ends without checking them in some way. And an alarm bell should go off in your mind whenever you see any kind of lensed optical equipment in a fiber optical plant. All trainers agree that the best way to check if a fiber is live is to connect it to a power meter. A few of them suggest that in the absence of a handy instrument, you can use a digital camera or the camera in a cell phone to see if the fiber is lit. The idea is that imaging sensors in these devices are sensitive into the near infrared where fibers operate. We say, check out your particular camera or cell phone on a known lit fiber before trusting it. Because the focal plane is farther from the lens for longer wavelengths than visible light, near-infrared tends to blur the visible image. Therefore, some manufacturers block the infrared with a filter. Be sure to check your camera or phone at the longest wavelength that can be present in your fibers. There are two general kinds of hazard associated with the infrared lasers used in communications: lasers themselves and light coming out of fibers driven by lasers. It is not that the light is so powerful, you are never dealing with so much as a watt, but the power can be concentrated in a very tiny area, and worst of all, you cannot see it. People who suffered eye damage by looking into an infrared laser have reported that the first thing they noticed was a popping noise inside their head. The pop was caused by a steam bubble forming in their eyeball. The infrared light is strongest right at its laser sources. It is also most easily focused from such sources, because the emitted laser light is collimated. Its rays are highly parallel, so the lens of your eye can concentrate the rays to a point. These factors make the laser sources particularly dangerous. On the other hand, usually laser sources are easy to recognize because they come in boxes: communication lasers, OTDRs, OLTS source and meter sets, and so on. Keep the output ports of these devices capped. Be certain they are turned off when you uncap them to connect them. Don't look into the port at all unless you are very, very certain it is powered down. There are standard classifications of laser power hazards as follows. Class 1 lasers are low-powered and completely enclosed, and therefore do not emit hazardous radiation under normal operating conditions. Class 1 lasers are exempt from any control measures. Laser printers and laser disc players are examples of this class. Class 2 lasers can emit accessible radiant energy exceeding Class 1 levels, but less than 1 milliwatt. Class 2 lasers are typically exempt from control measures other than having a protective housing and label. Class 3A lasers have power levels of 1 to 5 milliwatts. They normally would not produce a hazard if viewed for only momentary periods with the unaided eye. They can pose severe eye hazards when viewed through optical instruments such as microscopes, binoculars, or fiber inspection probes. Class 3B lasers have power levels of 5 milliwatts to 500 milliwatts for continuous wave lasers. These lasers will produce an eye hazard if the beam is viewed directly. At the high end of the range, even viewing reflections can cause harm. Fire hazards. If you do the calculation, 1 milliwatt spread evenly over the end of a 9 micrometer diameter fiber is 1.6 kilowatts per square centimeter. That's enough to get anything in contact with that small spot very hot, very fast. In many cases, fiber carries power levels higher than that. One should never clean an optical connector attached to a fiber that is lit. Optical power levels as low as plus 15 dBm or 32 milliwatts are known to cause explosive ignition of cleaning materials, such as tissue soaked with alcohol, on contact with the end of the optical connector. Hydro One operates some fibers that greatly exceed these power levels. Many other ignition sources exist around fiber plant working areas. Examples would be switches, some motors, curing ovens, and fiber fusion welders. Solvents are most prone to ignition because vapors can spread invisibly to ignition sources. Pay attention to good ventilation, minimize the amounts of solvent that can potentially get spilled, and avoid accumulation of other materials to which a fire could spread, such as paper. In summary of good laser safety practices, observe the following principles. Wear approved laser safety glasses. Never look directly into an unterminated fiber optic connector, either with the naked eye or with an inspection probe, unless you are absolutely sure there is no laser radiation present. Never look directly into uncapped optical ports when power supply is on. Keep the optical ports and the end of connectorized fibers either connected or capped while lit. Never look into a broken optical fiber cable that could be lit by the terminating equipment or test equipment, such as an Otdr. When working with fiber optic cable, always point the fiber to the ground to avoid deflecting the laser off any reflective surfaces. Know what equipment, for example IMUX, employs fiber optic lasers. Be aware of what is contained in the area surrounding your work area. Never use a direct view fiber inspection scope, other common microscope, or magnifying glass to look into the end of a live fiber. Safe habits must be established by self-awareness and repetition. Later, these good habits will save you from dangerous errors made in the complacency of routines.